Welcome to Lecture 1.2. In this lecture, I'll be discussing bonding as it applies in organic chemistry, introducing the concept of electronegativity, as well as the octet rule. Starting with bonding, a bond can be described as when two atoms are sharing their electrons. And this is going to depend on this concept of electronegativity. As brief review, as you go up and to the right on the periodic table, atoms tend to get more electronegative. And briefly, this means that they have a stronger pull on their electrons. So you can imagine this like a tug of war, where the higher the electronegativity, the stronger the tug of war player. So let's see how this plays in with bonding. There are three different types of bonds that you should briefly understand: the covalent, the polar covalent, and the ionic. A covalent bond is typically the case where two of the atoms that are bound are the same atom. So here we have a carbon-carbon bond. That means that they have the same electronegativity, and they're going to be a perfectly shared bond. Perfectly shared, right? Both are equally pulling. This tug-of-war game will never end. This is different from the polar covalent bonds, which we still view as sharing, right? Covalent basically means we're sharing our valence electrons. But what does polar mean? Well, here in the first case, we have a carbon-oxygen bond. The oxygen, being the more electronegative atom, pulls electrons towards it, which we use a dipole arrow, which is an arrow with a little line going through it, to represent. The idea here is that this oxygen is pulling some of these electrons toward it, and that this bond is biased towards the oxygen. One way we represent this is we put a delta negative, which indicates a partial negative charge. Not a full negative charge, but since that oxygen is pulling some electrons towards it, it's gaining a little bit of negative character. Now we can't just make charge like that. The carbon is losing electrons in the same way, so we can give that a delta positive. This is the term dipole, right? Like a magnet has a north and south pole, a dipole arrow indicates the formation of two different charges, or a dipole. When molecules have dipoles, we tend to call them polar. Now let's look at this next bond, the OH bond. This is another type of polar covalent bond, but sometimes it gets a unique name, which we call the hydrogen bond. This is because this same dipole, if you look at the difference of the electronegativity of these atoms, is quite large and leads to some interesting properties which we'll discuss later in the course. For now, we once again can see that the oxygen is the more electronegative atom, a delta negative and a delta positive. Now, ionic bonds are the extreme of this. We don't see too much of this in organic chemistry in terms of carbon, nitrogen, and oxygen, but it's useful to understand that we can refer to these generally as salts. And indeed, NaCl is common table salt. Here, we don't really view these as covalent at all. There's no sharing of electrons here. We have a chlorine that has taken all the electrons on from the bond, and that's why it has a negative charge. Whereas the sodium has a positive charge, it's lost all of its electrons in this bond. So it is still a bond, but notice that we do not use this line to represent it, because that is the line we use for covalent bonds. An ionic bond is simply an interaction in a crystal, right? Like we can think about salt that way. And these are typically very strong bonds, very hard to break, right? Melting salt requires a very, very high temperature. So with that in mind, we can see that different kinds of bonds form based on the electronegativity of the atoms and the difference between them. The most important thing to take away here is the formation of these dipole charges and being able to predict them when you're looking at a bond. This is going to be something that comes up again and again. So, one more thing to quickly discuss about bonds is the concept of multiple bonds. We'll go into much more detail on this in the Lecture 2 series about hybridization. But for now, I just wanted to introduce the idea of the single bond being what's called a sigma bond. So this bond is a single bond, right? These carbons share two electrons in the bond, and we call this a sigma bond. Note that the one thing to know about them is that they can rotate. Right? These bonds rotate freely. Now, what's interesting about a double bond is that it's not two of the same bond. It's not two sigma bonds. There's always one sigma bond under every single bond, right? In the double bond and the triple bond, there's always one sigma, And the extra bonds, we call these pi bonds. Right? These, main thing to know about them, is that a pi bond cannot rotate. We'll discuss why in more detail once we talk about hybridization. The same trend occurs with the carbon triple bond. We have one underlying sigma bond and now two pi bonds. Now that we've covered that, let's go into the octet rule. The octet rule states that each atom, and specifically in organic chemistry, we'll be referring to carbon, nitrogen, and oxygen. Right? This does not include hydrogen. Each atom must have 8 electrons in its valence shell for stability. Now, when we talk about electrons in the valence shell, what we really mean is just the electrons around the atom. When we talk about the octet rule, we don't care if those electrons come in the form of bonds or lone pairs. We're going to treat bonds and lone pairs as if they're just 2 electrons each. We're ignoring the fact that bonds are being shared. This won't be the case when we discuss formal charge, but when we talk about the octet rule, we're just asking about what's around each atom. So here's an example molecule. We can look at this oxygen here. Right? We see that it has 2 different lone pairs and 2 bonds. Each of those represents 2 electrons, giving you a total of 8. Right? Now these lone pairs, we could view them that they belong to the oxygen, whereas these bonds are being shared. But that's something we're going to talk about with formal charge. When it comes to the octet rule, we're just happy to see 8 electrons around that oxygen. That's great. It obeys the octet rule. We can look at this carbon here, for example. We see that it has 4 bonds around it. Each of those bonds represents 2 electrons. So once again, we could say that that carbon has a full octet, which makes it stable. Even looking at a double bonded carbon, right? A carbon that is connected with a double bond. We see that it too has 4 bonds connected and a total of 8 electrons. So if you're wondering if an atom that you've drawn is stable, always make sure that there's the octet being followed. Now, this is a very common rule, but I do need to note that there are a couple exceptions. So 3 exceptions I want you to know about. The first is boron. This won't be too common in OChem 1 material, but it's good to be aware of it. Typically, I see this tested mostly with just the octet rule, not really brought up afterwards. Boron actually wants 3 valence electrons, which we can discuss later when we talk about formal charge. But this means that boron actually only wants 6 electrons. So it's stable with 6 electrons around it, meaning that this is an octet violation. It's underfilled. However, it's an exception to the octet rule. This is what boron is stable with. Another much more important exception is this concept of the carbocation. The carbocation is a carbon that is missing an electron. In this case, if we had a hydrogen here, this carbon would be happy. It would have 4 bonds, a full octet, but we took away those electrons. And now we have a carbon with a positive charge. Okay? These are extremely unstable, as we would predict, right? This is a violation of the octet rule. However, they can exist in reactions. Right? Just because it's really unstable, right? That means it's never going to be a product. We're never going to have this in a vial, but it could be an intermediate in a reaction. And we're going to see that later in the course. So I wanted to introduce that concept now. The reason why these are so unstable is due to the octet violation. This third example is just to bring up really quickly. The octet rule is really more of an octet suggestion once you move away from organic chemistry. So again, carbon, nitrogen, and oxygen being the big atoms we focus on. So you can see examples here where sulfur and phosphorus have more than 4 bonds around them and violate the octet. We can call this an expanded octet. Typically, you're not really going to worry too much about this in this course, but in case you see it, just be aware this is another octet violation.